Okay, hi everyone. So we'll get started with our late afternoon session. This is going to be a student talk by Shijun Sun from UC Santa Cruz, who is a student of Sergei Sezuna. And she will be talking to us about interaction disorder duality and unconventional phase transitions. So this is a 12 plus 3-minute talk. So Shijun, take it away.
Thank you. So hi everyone. My talk today will be based on this work in progress with my advisor, Sergei Sezuna. And I'm a student at UC Santa Cruz, and I'm a graduate student at UC Santa Cruz, and I'm starting a postdoc position at Georgia Tech Institute. So in this talk, I'm going to tell you about an equivalence between two seemingly very different types of systems. On the one side of the system is interacting system without quench disorder. On the other side of the system is disordered non-interacting system. So at first glance, you might already say that it is not possible because on the one side, there are many body problems. On the other side, there's only a single body problem because systems is non-interacting. So how could this be possible? So our claim is not that all interacting systems can be mapped to disorder systems. What we are claiming is rather interacting systems, a subset of interacting systems that satisfy certain constraint can be mapped to disorder systems. So the constraint is low density of states at chemical potential. Systems that satisfy this constraint are, for example, nodal semimetals, by which I mean, in general, semimetals with band touching at a point. For example, graphenes, well-Dirac semimetals, and so forth. And also dilute gases with parallel dispersion. These systems can be mapped to a disordered non-interacting system at one dimension higher, which will become clear in a moment. So why is this interesting? First, it allows us for easier simulation of many body effects by mapping them to the disorder side to single body problems in the disorder side. Secondly, it allows us to predict new type of phase transitions by mapping existing ones from one side to another. So coming up, I'm going to show you more details of this duality, and then I'm going to show you 3 examples of the unconventional phase transitions that we are able to find using this equivalence. So before I get into the details, let me first give you an intuitive understanding of why these two sets of the systems can behave similar to one another. So for those of you who are unfamiliar with systems with quench disorders, don't worry, I'll give you a very brief overview of what it is. So why do we care about systems with quench disorder? When we theoretically modeling a system, what we have in mind are often perfect systems without defect. However, in real materials, there are defects in them, and the question is, how do we model them? Well, we can model them very simply by this Hamiltonian. So very simple, kinetic term, potential term. Now, when I'm writing down this Hamiltonian, I'm not just writing down one Hamiltonian, but a sequence of Hamiltonians, each with a different form of the random potential. Okay? So what is not known are the exact forms of the potential. What is known are the statistics of them. For example, the average of them and the correlation between them. So physical quantities are going to be depend on the Hamiltonian, which depend on the random potential, which sounds like a disaster because we don't know much of them. However, the quantities that we care about are so-called self-averaged quantities. And for those quantities, when we experimentally measure them, what we measure are the disorder averaged value of those quantities. By disorder averaged value, I mean you compute this quantity of each copy of the Hamiltonian, take many copies, average over them, that's the disorder averaged value. So let's think of a very basic picture. So this is just meant to be an intuitive understanding, it's not rigorous at all. But let's think of a 2-dimensional landscape of the quench disorder. Let's take one copy of them, say this one. And let's say at some point there's a particle coming into this disorder potential, and let's assume that it will follow some trajectory. And the question is, what trajectory will it follow? Well, it will follow a trajectory that takes least energy, for example, this one, which is following the valleys. Now, at some other point, some other particle coming in, see this yellow particle over here, it comes in and it will also say that this is the path that takes this energy, so that's the one it will follow. Now we take many copies of this disorder potential, average over them. We will forget about where are the hills and valleys because we have averaged over them. However, what we remember are that particles seemingly want to move along the same path. So this can be, so they seemingly want to move closer to one another. This can be modeled by an effective attractive interaction. So in summary, average disorder lead to attractive interactions. But this is not really an interaction because it's quenched disorder. The particles moving in the disorder potential are not going to give a back action to the potential. But if I were to draw Feynman diagrams that describe what I just said, it's reflected by the fact that there are a certain type of diagram that don't exist in the disorder side. And those are diagrams with a particle loop. So if you are familiar with replica method, this diagram is, because of the particle loop, this diagram, the particles running in the loop are going to carry replica index, which is being summed over. And this is why this diagram is proportional to the number of replicas. And in the end, the number of replicas is taken to be 0, so this diagram drops out. If you use other method to compute this, you will always get the same result that in disorder system, a diagram with a particle loop is going to disappear. As it should be, because this diagram corresponding to the particles, a creation of particle Hall pair screening the disorder potential, which do not exist for quenched disorder systems. Now, our claim is that if we can neglect this type of diagram in the interaction system, then we can map them to disorder system. And what are the systems that this diagram are suppressed? Well, those are systems with low density of states as a chemical potential. Why is that? This diagram corresponding to a creation of particle Hall pair. Because of Landau-Fermi-Liquid theorem, it's always created near the Fermi surface. So when the density of states at the Fermi surface is low, then they are going to be suppressed. So systems with low density of states at chemical potential are, for example, nodal metals, dilute gases, and also for systems who do not satisfy this constraint, for systems who do not have a low density of states as a chemical potential, if the process that we consider have a sequence of diagrams that's dominant, which do not involve a particle loop, then we can still map them to disordered system. I will give you an example in a moment. So I'm not going to go into too much detail of deriving the duality, but I'm just going to show you how the disorder set looks like. So the disorder system is one dimension higher. The reason it's one dimension higher is because when we write down a field theory for disorder system, there's only spatial directions. Whereas when we write down a field theory for the interaction system, there is Maslow time direction. So in order to map the Maslow time direction to the disorder side, we need an extra spatial direction to account for the Maslow time direction. And this is here. The momentum along the extra direction is mapped to the Maslow frequency. And also notice, you might ask, is it a specific form of interaction can be mapped to disorder system, or is it all form of interaction can be mapped? So in general, a general form of interaction finite range can be mapped so long as the form of interaction is mapped to the form of disorder correlation. And also note that this Hamiltonian have a pseudo-spin degree of freedom, which is described by this 2x2 Pauli matrices. I'm not going to go into the detail, but I will just highlight that we are able to derive this equivalence to all orders in perturbation theory.
Sorry, the interaction is repulsive? Or?
I will talk about that in a moment. Well, I will talk about that after my talk, if that's okay. Okay. Let me skip that slide and let me talk about disorder-driven transitions that we are able to find. Now, you might, for for those of you who are more knowledgeable, you might have already got a question. Isn't non-interacting disorder system only have one type of phase transition, which is the Anderson localization transition? It's not. There are actually more types of disorder-driven transition in non-interacting disordered systems. And we are able to find them by mapping existing interaction-driven transitions to disorder side and find those transitions. One example is bosons at 0 temperature with attractive interactions and power law dispersion. At dimension higher than alpha, where alpha is this power of dispersion, there is, when we do RJ analysis, we can draw this diagram where this axis is the strength of interaction. There is a critical value of interaction below which the renormalization group runs to 0, which means this phase is, in this phase, the system behaves as if it's non-interacting. Above the critical value, the systems are strongly interacting. The other parameter distinguishes the two phases are the number of particles, because on the one side, all particles condensate on the ground state because we consider low chemical potential, and that's why the number of particles is 0. On the other side, particles are strongly interacting, and they might form bound state before they condensate, and that's why we have non-zero particle number. We can map this diagram exactly to a diagram that describes exactly mapped to a diagram of disorder system, where now this axis describes the disorder strength. There is a critical value of disorder strength below which the system behaves as if it's disorder-free, above which the system is strongly disordered. Now I'm going to give you another example of phase transitions for finite Fermi surface. So for interacting system with a finite Fermi surface, the density of state is finite. However, if we consider BCS transition, near the transition, there is a type of diagram that's dominance, and those are the ladder diagrams, which do not consist particle loop. So what we can do is we can map this set of diagram to a set of diagrams in disordered system and map a 2-dimensional metal to a 3-dimensional nodal line semi-metal. And this way, we are able to find a disorder-driven transition for 3-dimensional nodal line semi-metal where there is a critical value for the disorder strength, below which the density of states as a chemical potential is 0, above which the density of states broadens, the nodal line broadens. This is a work of another grad student in our group, Siyu, and my advisor, Sergey. And do I still have time to talk about the third? Okay. Okay, wonderful. So the third example I'm going to give you is the following. So look at the Hamiltonian for the disorder side. There is an isometry along the actual dimension. How do we make them more how do we make all directions the same? Well, the way to make them the same is by making the size of the actual dimension to be small. So a dimensional reduction, if you wish. In that case, this momentum along the actual direction is going to, only the 0 mode is going to contribute the most. And the Hamiltonian is effectively reduced to this Hamiltonian, which have a disorder-driven transition studied by these authors. We can now map this transition to a interaction-driven transition for the interacting system at very high temperature, where only the 0 mode of the multiplier frequencies contribute. And you might think this is not realistic, but let me give you 2 explanations of why this might be realistic. First, our motivation is from trapped ion systems. For trapped ion systems, compared to their coupling, their temperature is actually very high. Secondly, for any system, what we can do, so for any system at a certain temperature, there are energy modes that are higher than the temperature and there are energy modes that are lower than the temperature. What we can do is do an initial renormalization for the higher energy mode and get an effective field theory whose cutoff is lower than temperature. Then we can do RJ for this effective field theory and find this transition. And next up, I'm not going to go into the detail, but we have an example system which exhibits this phase transition. And with that, let me just give you the takeaway message. The interaction system with low density of states as a chemical potential can be mapped to a disordered system with one dimension higher. And we are able to show this equivalence to all others in perturbation theory. And this equivalence can be used to predict more phase transitions. Thank you. Sure. Yeah.
So, like, especially in this context, what does strongly disordered?
Oh, strongly disordered. So so this Hamiltonian describes a nodal point semi-metal. For the disorder-free case, the density of states at the chemical potential is 0. For the strongly disordered phase, the nodal points expands and the density of states is finite. Yeah. And before the next question, let me answer the question about repulsive interactions. What I did not tell you about is another way of intuitively understanding how it works. And it's supposed to be an intuitive understanding, so it's also very easy. Let's starting from the interacting system and decouple the interaction, use a Hubbard-Stratonovic transformation, okay? And then this partition function resembles a disordered system where this part are the disordered system with phi being the impurity potential. And this part describes the correlation between the disordered system. Now you might already say, wait a minute, this is not really a disordered system because now if we integrate out the particle field, then we will get a determinant. However, for systems with low density of states, for systems where we can drop all those bubble diagrams, those diagrams with particle loops, then this determinant is going to be suppressed also, and therefore we can map. And we map that into a disordered system with the form of disorder correlation being described by this form. Now, if we were to take this part to the disorder side, we would have write down a Hamiltonian looks like this, right? Which seems to be fine, but if we do a Hermitian conjugate, it's non-Hermitian because this part is Hermitian, this part is anti-Hermitian. We can stop here and say, okay, interaction system is mapped to disorder system, which is non-Hermitian. However, we want to try manage to map it to a Hermitian system. So the way to do that is by a hermitization procedure, where we basically double the Hilbert space and multiply the Hermitian part of the Hamiltonian with a polymatrix and multiply the anti-Hermitian part of the Hamiltonian with a different matrix. Now, this Hamiltonian is going to be equivalent to this non-Hermitian Hamiltonian that we start with if we are talking about zero energy states, which are the states that we care about in our mapping. So now I showed you a hermitization procedure. Now let's get back to the Hubbard-Stratonovic transformation. Here you can also say that only attractive interaction so we can only do Hubbard-Stratonovic transformation for attractive interactions. If we were to do the same thing for repulsive interactions, we will need an imaginary HS field. However, since I told you about the hermitization procedure, the imaginary field does not look so crazy because we can just hermitizing it by simply multiplying the polymatrix that are the same as the first term rather than the polymatrix that are the same with the second term. So both attractive and repulsive interaction can be mapped.
So in the vinyl semi-metal case, there was an issue about the rare events, rare effects, physics. Does that come in this analysis?
Thank you for bringing this up. So our mapping itself only accounts for the perturbative effects, the rare region effects coming from the non-perturbative effects. So we are not able to take them into account. Therefore, the phase transition I'm talking about here, there are possibilities that the rare region effect could turn this phase transition actually into a crossover. Yeah.
So does the Anderson transition in the disorder system correspond to anything in the lower dimensional interaction system?
Great question. So at first thought, I might say that's a little bit hard to map because for Anderson localization, there's a finite Fermi surface. But if we are looking at the diagrams, if we can find an interacting system where the sequence of diagram that's similar to the Anderson the diagrams describe Anderson localization, then yes, we can map them. But we have not considered that yet. It's an interesting future direction.
I have a question myself. So in the strong disorder limit, somehow you're getting some sort of condensation or some superconducting condensate. Typically, when you think of superconductivity, it's almost, it competes with disorder. So disorder is not good for superconductivity. How would you understand that?
Yeah, so we are mapping the transition to a disorder-driven transition, but we're not necessarily mapping the superconducting states to a superconducting states. What we are mapping is this, are the phase diagrams, but what we are not mapping are the each phase of the previous system.
There are no more questions this time, Shijun, again, but it was a nice talk.